So in Chapter 9, what we're going to do is we're going to talk about IPSec, IP security. IPSec is actually not a protocol. It is a standard of protocols that we use to ensure IP security. Now, most people, when they think of IPSec, they associate that to VPN, and that's usually what it's related to. So we're going to see some of the different standards that we use to ensure connectivity. We're actually in this chapter going to do a deep dive into the Diffie-Hellman key exchange process. We're going to talk about IP1, IP2, and so on. So let's say that I want to establish connectivity from a branch office to my corporate office or business partner. I'm going to use IPSec or cryptographic VPN to connect. Now, VPN by itself, the term VPN kind of connotes this idea that you're doing encryption, right? And that it's a secret network and it's the data that's passing over this network is hidden from being intercepted and viewed. But VPN doesn't necessarily mean cryptography, right? A frame relay network is a VPN. MPLS is a VPN, and it doesn't employ the use of cryptographic standards. But what we're going to talk about with respect to VPN is a cryptographic VPN, where we have endpoints that establish sessions with each other, and over those sessions we're using cryptography, message integrity algorithms, anti-replay protection, non-repudiation of origin, authentication, and so on. So there are under the guise of cryptographic VPNs, there are two different types of VPNs that exist: a site-to-site VPN and remote access VPNs. So site-to-site VPNs tend to typically be something that's permanently established between gateways, between different endpoints, whereas remote access VPNs are temporary, and we're going to access resources through remote access VPN on a temporary basis. And then we have the ability to run IPSec versus SSL. Now, SSL is typically going to be related to a client VPN solution. We saw this when we were kind of going through the lab exercises earlier. We talked about clientless SSL versus client-based SSL. What is the difference between clientless SSL and client-based SSL? An application versus a browser. A thin client like AnyConnect, Cisco AnyConnect, versus a browser, right? In client-based SSL VPN, the desktop or the host or the machine that's connecting to the VPN has a thin client installed, and we utilize that client to connect securely to our infrastructure. In a clientless SSL VPN environment, we are using a Windows browser or a operating system browser to actually access the IP address of the portal that we're connecting to, and we establish our SSL tunnel or TLS tunnel or whatever it might be over through the web application. The downside to using a clientless SSL as opposed to client-based SSL is support for native applications. Right? If you're using a web-based SSL VPN, you might not be able to use all of your native desktop applications. You might have to use these things called application plugins or Java plugins to be able to do things like remote desktop, SSH, Telnet, and so on. All right. Site-to-site VPNs are typically permanent. Now, most site-to-site VPNs use IPSec. You can establish site-to-site VPN communication with other VPN technologies, but for the most part, we're going to stay with IPSec. All right. And we'll talk about the differences as we go through the chapter here. IPSec security services include confidentiality, ensuring that the data that's being transmitted and received is hidden and it can't be read. In other words, it's being converted to ciphertext. Data integrity, right? Confidentiality, we use encryption algorithms. Data integrity, ensuring that the data arrives at its destination unchanged, right? Not modified when it reaches the destination. Origin authentication, pretty much identifying that the source of the information is trusted and the source of the information is verifiable. We call that non-repudiation of origin, or simply authentication. Not authenticating the destination, but authenticating the source of that traffic. Then we have anti-replay protection. Verifies that the packets are unique and they haven't been duplicated, right? So anti-replay literally means somebody's in the middle of the conversation, they're copying my data for the purpose of cryptanalysis or whatever it might be, and then they're sending the data on its way to the destination. We have protection mechanisms in IPSec that can detect whether or not that occurs, whether or not data is being copied and replayed, okay? Key management, a very important aspect to any IPSec environment. Not only establishing the initial bulk encryption keys, but also over the lifetime of that VPN session, terminating or destroying old keys and regenerating new keys that are used, because we do like to do key rotation. We perform key rotation for our IPSec VPNs because we want to essentially ensure the security of our keys. If somebody is trying to decipher a key, maybe after a certain period of time, they've identified certain aspects of the key. If we simply rotate the key, now all the work that they've done to discover those certain aspects of the key becomes invalid and they have to start all over again. All right? So key management is not only the initial exchange of our keys, but also the rotation of keys, or the destruction and reproduction of new keys during the encryption process. We talked about in a previous chapter how symmetric algorithms are used for bulk encryption. Why are symmetric algorithms used for bulk encryption? Because they're efficient. They can be run in software. They don't require a lot of resources. We can send large amounts of data, but still ensure confidentiality. So DES, triple DES, AES, SEAL, these are all of our primary bulk encryption algorithms. Most people kind of sit in this space right here. The advanced encryption standard is what we typically use today. Okay? The advanced encryption standard comes in different variations. It's a block cipher, takes blocks of input data, cipher, plain text, goes through 11 rounds of encryption. You've got the main round, then you've got 9 middle rounds, which are duplicate rounds, and then you've got your final round. Now the way AES works is it takes your plain text data, it does XOR operations, so it does some Boolean math with the key. You have your initial round key, and then for each of the additional 9 rounds, you have a different round key for each round, so the key changes not only through the process, but then we're also taking our output data from our previous encryption process, and we're using that as our input data for our next encryption process. So it's a very, very interesting protocol. If you go out to Google and you search on AES simulator, you'll find several out there that actually simulate the whole process, and they walk through the whole process, right? Some of the things that are part of this process of these different rounds, shift rows is one of the, there's 4 different steps that go into each round. Shift rows, mixed columns, modular math, and then there's an XOR operation with the round key. But it's a very interesting process, okay? With IPSec, the initial challenge with establishing a secure channel over an insecure environment like the internet is, how do we establish the initial key? How do we establish the bulk encryption key that we're both going to use, the shared secret key? Now there's a couple of ways that you can do this, but the primary way is to use something called a key exchange algorithm. Diffie-Hellman is that key exchange algorithm. The way Diffie-Hellman works is we have a set of numbers or variables that are generated by each of the participants in this IPSec environment, and we have an exchange of information. We'll see it on a slide in a little bit, and through that exchange, we're able to derive a shared secret key without actually publishing that shared secret key. All right. So we have Diffie-Hellman algorithms, and then we have the more advanced elliptical curve Diffie-Hellman algorithms, which are much more secure. All right. And we'll see how Diffie-Hellman works here in a few minutes. For data integrity, we use our hashing algorithms. We've been talking about hashing algorithms in a lot of different sections here. A hashing algorithm like MD5, like SHA, takes plain text data, inserts it into the hashing function, and in the case of HMAC, we insert secret keying material as well, and we come up with a fixed length authentication hash output called the message authentication code. The purpose of the hashing algorithm within the confines of IPSec is to provide for two things: authentication and message integrity, or data integrity in this case. All right. These are all just the building blocks of IPSec. For authentication, we use various authentication methods. Now remember, we're talking about IPSec, which is directly related, well, specifically cryptographic VPNs, which is directly related to establishing a tunnel between two endpoints. Now, before I can establish a tunnel between two endpoints, I have to ensure that I'm authenticating the peer. So when we talk about authentication in this case, we're not talking about authenticating the data. We're not talking about authenticating a post IPSec tunnel encryption establishment. We're talking about an initial peer authentication process. In most cases, we're going to use PSKs, pre-shared keys. These are tunnel keys. They're not keys that are used for encryption. They're not keys that are used for key exchange. They're just simply keys that allow us to identify the identity of the peer or verify the identity of the peer. These are pre-shared keys. The reason they're called pre-shared keys is because you configure them on each endpoint manually, and when you're trying to establish the configuration for your VPN. You do have the option of using public key infrastructure using RSA signatures, right, where you have a public and private key exchange process to do your authentication. You can do encrypted nonces. What is a nonce? It's something that's only used once. That's literally what it stands for. Okay? Nonce is something that we only use once. So we have maybe a token or some sort of key that we use once to verify the authenticity of the peer. Or we can use elliptical curve DSA, which is the digital signature algorithm, which is very similar to the RSA process. It's just more of a modern protocol, and it's more secure. Okay? So we need to authenticate our peers. Then we can go through the process of negotiating the IPSec and ICKMP information. So IPSec as a suite of protocols looks like this. Your IPSec protocol, well, these aren't really protocols. ESP is not really a protocol. ESP plus AH is not a protocol. AH is not a protocol. These are different ways to implement IPSec. AH stands for authentication header, meaning that you're not going to have any encryption because we're only concerned about authentication and maybe some message integrity. If you're running ESP, you're primarily concerned about encryption. You're not necessarily concerned about authentication. So in most cases, we're in this space right here. ESP plus AH, meaning we're running encryption plus authentication. These are our encryption protocols for confidentiality. These are our hashing protocols for message integrity. Remember, SHA-2 is 256 bits, 384 bits, 512 bits, etc. And then we have origin authentication using pre-shared keys, RSA, elliptical curve, DSA, etc. And then we have a key management protocol that allows us to not only establish the security parameter indices and the security association profiles, but it allows us to establish a shared secret key and identify the lifetime. It helps us identify the lifetimes of the keys and et cetera, et cetera. Okay? So you've got the Diffie-Hellman key exchange process, elliptical curve Diffie-Hellman, the Internet Key Exchange Protocol, or Internet Key Exchange Protocol version 2. We'll break these down as we kind of go through the rest of the lessons here. Okay? This is IPSec. IPSec, even though it's always listed as a protocol, is really a framework of a whole bunch of different protocols. And by putting these pieces into place, we're ensuring secure communication between our endpoints. So what is the Internet Key Exchange? The IKE protocol automates the initial key exchange process. All right, we have these things called SA parameter negotiations. SA stands for Security Association. Essentially, it's the parameters of the tunnel of the encryption that we're going to be running to secure our traffic. So there's a key generation process. We do our peer authentication using pre-shared keys or RSA, and we do our key regeneration process if the keys expire or the keys are no longer valid. All right. Now there were some limitations of IKE v1. So IKE v2 was developed to handle a lot of those limitations. It's kind of beyond the scope of this class to talk specifically about what those limitations are, but you can see here it requires fewer transactions, so it's faster. It has extensions for doing dead peer detection, NAT traversal, so allowing this IKE authentication to go through different NAT boundaries. Dead peer detection, identifying when the peer is no longer responding or no longer available, so we can essentially expire our VPN connection. Has stronger security, so there's denial of service protection, other functions that protect the protocol itself. It's much more reliable, so it has sequence numbers, acknowledgements, a lot of error correction mechanisms built in. It also has support for something called the Extensible Authentication Protocol, which is what we typically associate to like 802.1x. In wireless networks, we see a lot of extensible authentication, and it also supports mobile layer 3 roaming. And again, I'm just kind of reading bullet points here. There's a lot more involved. Some of these are pretty easy to understand. Some you may not understand, but it's not really that critical right now. All right. So let's go through the process of how routers establish a VPN tunnel between each other, and then we'll look at the actual configuration a little bit later on. So I've got a router on the left, wants to establish a VPN tunnel to the router on the right. Now there are essentially two phases of operation that occur here. There's phase 1, which is the initial ISA-KMP and IKE phase, right, where we're doing our security association key management, and we're establishing our SA parameters. And then there's phase 2, which is our actual bulk encryption phase. That's where we're establishing the IPSec tunnel. That's where we're identifying the keys that are used for bulk encryption, and we're establishing that bulk encryption tunnel. So we always troubleshoot VPNs in two phases, phase 1 and phase 2. All right. So the first step, and this is just a general representation of this, we'll get into the details of this as we move through the slides here, is to do your first initial key exchange negotiation. All right. So we're going to say, router A is going to say, okay, I want to establish a tunnel with you. These are the parameters of the tunnel that I want to use. The lifetime of the keys, the Diffie-Hellman key exchange protocol that we're going to use, the encryption protocol we're going to use, the hashing algorithm we're going to use, et cetera, et cetera. And then router B is going to agree on a particular policy so that we're both speaking the same language. And then we go through our key exchange process. This Diffie-Hellman key exchange process is the process that allows us to establish our bulk encryption key, the key that we're going to use for the bulk encryption process. And then we're going to authenticate our peers and establish the security association profile, and we'll have our tunnel established at that point. Yes, sir.
So you say routers, a host with a client on it can do this as well, correct?
It can, but most of the time clients are going to be using some sort of SSL type of solution.
Okay.
Back in the day, clients used to use an IPSec solution for remote access, right? When Cisco had a VPN client that was IPSec based. Any Connect can still do IPSec, but SSL is different than what we're seeing here.
Okay. So nowadays, do you typically see this with site-to-site VPN?
This is for site-to-site VPNs, firewall to firewall, firewall to router, whatever it might be.
Is there a big reason behind that change, or is it just kind of simplicity sort of thing?
Well, SSL VPN is a lot more flexible because we don't have to be tied to a client at that point, and that's really the key, right? IPSec VPN always required some sort of thin client to operate. You couldn't establish an IPSec VPN session using a web browser. You would have to use a client. So we saw the shift to SSL VPN for that reason. I mean, there's other reasons, but for that reason, because we had the ability to operate in a clientless environment as well.
Okay. But again, clientless does have its limitations.
It does, yes. Clientless does have limitations. Now, Cisco and other vendors have come up with solutions to those limitations, right? Doing smart tunnels and application plugins and stuff like that. But it does add to the level of complexity of the configuration too, because you have to configure all that on the back end. Okay, so we're going to take a look at this first box or this first set of transactions right here. All right, these are the three primary transactions that happen in main mode negotiation for IKE. Now remember, when we talk about phase one, in phase one, we're not actually establishing our VPN tunnel. We're setting up all the parameters, but we're not actually establishing the bulk encryption. So we're going to break down over the next few slides this part, and this part, and then we'll get into phase two of the process, which is where we actually establish the tunnel itself. So the router on the the router on the left wants to establish the tunnel, and whoever is responsible for establishing the tunnel depends on where the interesting traffic is being initiated from. In this case, PC A wants to talk to PC B, so that router A is going to be the one negotiating this VPN tunnel. So what's going to happen is we're going to have a set of policies configured on the router statically, or the ASA, or whatever it might be that we're using for VPN. And those policies will have sequence numbers. Sequence 10, sequence 20, and there's really no preference to the policy because what A does is it sends over to B every single policy that it has. All right, A is going to send over to router B. These are all of the IKE phase one parameters that I can support. What encryption are we going to use? What hashing algorithm are we going to use? How are we going to authenticate each other as peers? Right? What is the key exchange protocol that we're going to use to establish our shared secret key? What is the lifetime of those keys, and when do we have to rekey? Right? So these are all the general parameters, what we call the SA parameters, Security Association parameters, that we're going to use to establish this IPSec tunnel. What happens then is B, once it receives all of the appropriate profiles, B is going to choose a profile based on parameters that match what A is capable of doing. So policy 200 on router B happened to correspond to policy 10 on router A. The policy numbers are local to the router. They don't have to match on each router. All right. So we are now, we've kind of negotiated, well, all of the internet key exchange properties that we're going to use to do our key exchange process. AES 128, SHA 256. We're going to do pre-shared authentication for the peers, and we're going to use Diffie-Hellman Group 5. to establish our shared secret key for bulk encryption. And the key is going to have a lifetime of 43,200 seconds. The seconds don't match here, so we're going to go to the least common denominator. Well, the smallest number, I should say, not the least common denominator. All right. So what is a Diffie-Hellman key exchange process? Now we're moving into this second phase, the key exchange process. This slide really does a very good job of kind of depicting this process. I can't take 100% credit for this slide. I can take about 80% credit for it because it's really kind of a conglomeration of a bunch of different things I found online, and I pulled out the best parts of what I thought would be useful. Okay? Let's look at it from a generic sense first. All right? We don't need to look at the math of it yet. Let's just look at a generic sense. All right? So Alice and Bob, these are the endpoints that are trying to establish a session with each other. They have something called a common paint. Now that common paint is a generator number and a prime number. And we can see that as G and P. So G equals 7, P equals 11, G equals 7, P equals 11. That's sent over the channel in plain text. Nobody, we don't care that anybody knows that number or those numbers, okay? Like I said, P is your prime number, G is your generator, and of course P has to be greater than G, and G is a primitive root of P. All right? I'm not going to get into all the math of that. It's not necessary for this class, but these are numbers that are calculated and generated during the process of establishing this shared secret key. So think that Bob and Alice both have a bucket of yellow paint. That yellow paint is their common paint. Alice is going to generate a random number, X sub A, and that is going to be Alice's secret paint. Bob is going to generate a random number, X sub B, and that is going to be Bob's secret paint. Nobody is ever going to know what the color of Bob's paint is except for Bob, and Alice's paint except for Alice. All right? Now, if you place that information into the formula, Y sub A, which is essentially the paint that we share in step 3, right? The paint that we share, the brown paint here and the blue paint here, Y sub A is a mix of the common paint and my secret paint. So Alice is going to take the common paint, yellow, mix it with orange, and it's going to come up with this weird color right there, a light orange. All right? And remember, two components of this formula are the same. G and P, which are the common paint, and the variable that only Alice knows, X sub A, and the variable that only Bob knows, X sub B, goes into the formula. Now, if I asked you guys and I said, hey, why don't you take a bucket of paint, take this yellow bucket of paint, and mix it with some other color and send me that bucket. Now, if somebody, Evil Eve, in the middle intercepts that bucket, is Evil Eve going to be able to derive the secret paint from that paint mixture? How difficult is it to unmix paint, right? It's practically impossible. And mathematically, in that same vein, because we're dealing with very large prime numbers and random numbers and whatnot, these calculations are irreversible. So even if Evil Eve sees Y sub A and Y sub B, even if Evil Eve sees Y sub A and Y sub B, it doesn't matter. All right? Now this is the best part of this. Bob took yellow paint and mixed it with green paint, and then mixed it with Alice's mixed paint, which, by the way, was also yellow paint, but it was Alice's orange paint. So Bob ends up getting this common paint color. Alice is mixing yellow paint with orange paint with the light blue paint that was sent from Bob, and is taking that light blue paint and mixing it with their private paint. In the end, they end up with the same paint color. So there's two ways to look at this, right? There's the paint color way, which is a very basic concept. Each of them are mixing 3 paint colors. But the third paint color that's being mixed, the second paint color, is a result of the other 2 paint colors from the other party being mixed, the private and public paint. So in the end, when it's all said and done, they've all mixed the same colors. Just in different orders, that's right. And that ends up resulting in this common secret color, which is never shared over the public domain, which ends up being our pre-shared key, our bulk encryption key, not our pre-shared key. Now, if you look at it from the mathematical perspective, it's essentially the same thing. Y sub A equals 7, 6 mod 11, which equals 4 in this case. Y sub B, 7 to the power of 9 mod 11, which equals 8. I'm not going to get into the modular math aspect of it, but trust me, those values are correct. And by the way, we're dealing with much, much larger numbers in real life, obviously. All right. So you'll notice that we have a private and a public value. The private value is X sub A, which is the secret paint. The public value is Y sub A, which is a mixture of the secret paint and the common paint. All right. It's a very interesting concept because the way that we're establishing a shared secret key over a public domain, yeah, I guess your books are in black and white, so it's a little bit harder to see the colors. I didn't think about that. I saw you coloring everything in. I was like, yeah, you have this in a PDF that was sent to you on day 1. If you can't find the link, let me know. Sorry? PDF's in the OneDrive. Oh, it doesn't have this slide. Does your book have the slide? That's weird. The PDF doesn't have it, but your book has it. I will make sure to put the updated PDF in the OneDrive for you guys. All right.
Take a picture of that.
So you guys may have heard of the Diffie-Hellman key exchange process before, but maybe you didn't realize that this is how it works. It's a very interesting process. That's a very, I can't claim that myself, but that's a very common way that people reference that or metaphorically reference the Diffie-Hellman key exchange process. All right. So the third exchange. Now we've done the first 2 exchanges. We did our initial negotiation of the policies that we're going to use. We've done our key exchange. Believe it or not, all of this occurred before we even authenticated each other. So it's kind of like the horse after the cart, right? Because we've gone through and we've done all this setup of our security associations, but we haven't verified the identity of each other. So we still haven't identified whether or not we can even establish an actual tunnel with each other. So the third exchange is to authenticate the peer. You would think that you'd want that to be the first exchange, but it's not. All right. Now, the most common peer authentication method that you'll see in most VPN solutions is to use a pre-shared key. But like we said, we can use RSA, encrypted nonces, or ECDSA signatures. Okay. If for some reason I can't authenticate the peer at this point, the authentication fails, the security association parameters that we just spent all that time negotiating get thrown away. All right?
Yeah, so the second exchange gave us an opportunity to share data, encrypted data.
In what sense? What do you mean?
Well, because once we finished the second exchange, we then had a bulk encryption key.
Yes,
Right.
but we still haven't authenticated
No,
each other as
but now
peers.
that we have an encryption key that only we share, now we can send the pre-shared key without concern that it will be compromised.
Right, right. Well, and remember, with the pre-shared keys, we're never really sending the pre-shared key.
So,
We're generating hashes and verifying hashes and whatnot to see if the key is so. But you're right. At this point, we have what we need to establish our encrypted session. Once we've successfully verified the identity of the peer, we move into phase 2 of the IPSec KMP process, which is to establish our bulk encryption channel. Phase 2 is IPSec. Okay? All right. So typically we will refer to phase 1 as an IPSec KMP essay, and then we'll refer to phase 2 as an IPSec essay. That's why when you're debugging this or you're trying to verify, you do a show crypto IPSec KMP essay. That's going to tell you whether or not you have an effective phase 1, and you can do a show crypto IPSec essay to see if you have an effective phase 2. Parameters. Now, IPSec, there are 2 main IPSec framework protocols. We talked about this when we looked at the overall framework itself. Authentication header, which is just an IP protocol, protocol 51, and ESP, what we call encapsulated security payload. ESP is the encapsulated security payload. That's protocol number 50. AH does 2 things, authentication and integrity. That's all it provides. There is no confidentiality, there's no encryption, and in most modern IPSec VPNs, this is not used. Because most modern IPSec VPNs also want to have data confidentiality. They want to make sure that the data is encrypted. All right? So ESP provides data integrity, anti-replay, origin, authentication, etc., but it also provides confidentiality. All right? So here's a visual representation of what authentication header looks like. I have my IP header, I have my payload information, I have the key that I'm using for the authentication component. I run that through my hashing process, I come up with a MAC, and then I simply encapsulate that hash into an authentication header payload. The IP header and the original data is sent in plain text over the internet. This is very similar to what you would see with like routing protocol authentication, where the routing protocol messages are sent in plain text, but the data, but we've got this encrypted hash that allows us to verify the integrity of the data, because the data and the header are part of the hash, or the initial data that goes into the hash, and then we have a key which provides that authentication. Starting to see a lot of similarities between these different processes, right? ESP, which stands for Encapsulated Security Payload, allows us to add encryption on top of that. So we take our IP header and our data. That information gets encrypted. So we've got an ESP header, we've got an ESP footer, our authentication field, IP header, data field, and essentially everything is encrypted and transported in a new IP datagram. Now, whether the original IP header gets encrypted and a new header gets generated, or the original header gets copied outside of ESP, depends on what mode of ESP you're running in. There are actually 2 different modes of ESP, tunnel mode and transport mode. Okay? I'll explain the difference here on the next slide. Tunnel mode, first of all, is primarily the mode that we use for IPSec site-to-site VPNs. Meaning that the original IP header is encapsulated inside of ESP, the data is encapsulated inside of ESP, and then all of that information is encrypted. So my original IP header is encrypted, my data field is encrypted, and then I've got my ESP header and my ESP footer. And then on the outside of that, I have my new IP header. So you can imagine there's quite a bit of overhead with this. You got your 56 bytes for ESP plus an additional 20 bytes for the internal header. So there's a significant amount of overhead here. If you imagine how a site-to-site VPN packet works, you've got two routers that are establishing some sort of VPN tunnel with each other. You got the PC in this LAN wants to talk to the PC in that LAN. These PCs have an IP address. Usually private IP addresses related to those particular subnets, right? This is a public domain, like the internet, and the VPN tunnel is established from this router interface to this router interface. And on those interfaces, there's public IPs. By the way, those are also my crypto interfaces that have the VPN configurations on them. So the data comes in from the client unencrypted. There's a crypto ACL that identifies that this traffic needs to be encrypted. A is pinging, as an example, A is pinging B directly. Of course, A and B have private addresses. That's not going to get routed over the internet, which is the reason why we need the VPN tunnel. Once that data reaches this crypto interface, that's when the encryption occurs. The original ping and the original IP header is still intact. The outside header represents the information that's necessary to get the data from here to here. It's the public header. The source address is the public IP address of the router that's doing the encryption. The destination address is the public IP address of the router that's going to do the decryption. So if you can imagine, this internal IP header is the header that was used by the original client, and this external IP header is the header that we use to get to route over the internet. Transport mode is typically used for remote access VPNs, remote access IPSec VPNs, where we're actually not recreating a new header. We're copying the old header or the original header outside of ESP and using that original header to do the routing. All right. Does this make sense? So now we move on to phase two. We've gone through the process of establishing phase one, which was in main mode negotiation. There's quick mode also, but we didn't talk about that. In main mode negotiation, 3 steps to establishing that phase one security association. Then we move to phase two. And in phase two, what we're trying to do is we're trying to establish a VPN tunnel, and a lot of people don't realize this, but we're actually establishing multiple VPN tunnels, a tunnel for traffic going from left to right, and then a corresponding tunnel for traffic going from the right to left. There are actually 2 unique separate tunnels that are created. It's not an individual bidirectional tunnel. It's a unique security association in each direction. And we call those SPIs, or security parameter indexes. Well, there's a number assigned to those tunnels called a security parameter index. But when you do a show IPSec, show crypto IPSec SA, you will see 2 different tunnels established. One outbound and one inbound. All right. All right. So let's take a look at the actual configuration. We could do this in GNS3, but let's just take a look at it. If you guys want to look at this later and build a little network in GNS3 to do this, you could. All right. So we're going to set up a tunnel from router A to router B. This is not an ASA. This is Cisco iOS. We're going to set up a tunnel from router A to router B. So the first step, what do you think the first step of establishing this configuration is going to be? Setting up your IKE Phase 1 proposals, the key exchange proposals. All right. Then step 2 would be to set up the pre-shared key authentication. Step 3 would be to set up your IPSec Security Association parameters. And then step 4 would be to apply it to the interfaces. All right. Now, why is that slide there? What happened to the configuration? That's weird. I guess we're not going to look at that right now. There used to be a whole configuration of that. All right. It's not in the book either. All right. Well, okay. We're not going to see that right now then. I apologize. I will make sure to add that to the updated materials, and I'll send that out to you guys. All right. But let me talk about what they're talking about on the slide here, because I want to at least kind of go through the steps that you would look at, right? You want to set up your IKE v1 proposal. So that's step number 1 is your IKE proposals. Step number 2 would be to set up your pre-shared key authentication, between the peers so that you can authenticate the peers. Step number 3 would be to set up your IPSec parameters. In other words, you're going to identify what type of encryption, integrity, etc. you're going to use for phase 2 of the process. Step number 4 would be to set up an ACL. Now, why would I want to set up an access control list? Because the access control list is used to identify what traffic goes over the tunnel. Remember, these routers have internet connections. Those internet connections are used to service regular internet traffic, but they're also used to service the VPN traffic. So we have this configuration called the crypto ACL. And the crypto ACL is used to identify what traffic goes over the tunnel as opposed to what traffic doesn't go over the tunnel when it leaves the interface. And then step number 5 would be to apply the crypto configuration to my interface. So I'll just put crypto interface. So we need to apply our crypto configuration to the interface. Unfortunately, that's not listed here, so I apologize for that, but maybe I'll update the material and send it out to you guys. All right. Now, we've moved over time, over the years, to new protocols, and we have what we call these Suite B protocols now that are used for modern cryptography. For confidentiality, the minimum recommendation is to use AES. Even though DES and triple DES are useful or usable, we're going to use AES. For integrity, we're going to use SHA-2. 256-bit SHA-2 at a minimum, to be exact. For authentication, we're going to use the elliptical curve digital signature algorithm. Okay? Elliptical curve digital signature algorithm as opposed to Diffie-Hellman and pre-shared keys, excuse me. And then for key management, we are going to use the elliptical curve Diffie-Hellman algorithm. All of these Suite B protocols, really the only changes, the only differences we see with these protocols is primarily the key space. The crypto variable is much larger with these cryptographic standards. Fundamentally, they're essentially the same algorithms. All right. All right. And in IKE v2, we talked about that already. Improved security, better performance, more flexible authentication options, so we can create additional authentication options for IKE v2 and so on. All right. So that is the end of that chapter, that lesson.